Hello class, and welcome to this example on related rates. We're going to be talking about pumping air into a spherical balloon and the relation between the radius of that balloon and the volume, but more importantly the relationship between the rates at which those two values are changing. What you already know is the relationship between these two values, volume and radius. Volume is 4/3 pi r cubed, and I gave you just a couple examples. Depending on the size of the radius, you can see how the volume changes, right? That's the relationship between the radius and the volume. But what we want to investigate in calculus is relationships between the rates of change of those two values, okay? And this is a typical related rates problem. So we're going to look at a problem. It goes like this. Air is being pumped into a spherical balloon at a rate of 5 cubic centimeters per minute. Determine the rate at which the radius of the balloon is increasing when the diameter is 20 centimeters. Okay, so we're going to follow a three-step process for every one of these problems. It goes like this. The first step is to just translate those words into math. And I always use I'm looking for three things: the formula that I'll use, what's given, and what I need to find. The next step is I'll take that formula and I'll differentiate it. And the third step is to fill in the blanks and solve for the unknown. Okay? So what do we have here? We have the volume of a sphere. I know the formula for that. We just talked about it. Volume is 4/3 pi r cubed. Okay, what's given? They say air is being pumped into a spherical balloon at 5 cubic centimeters per minute. I got to translate that into math. That is the rate at which the volume is changing, right? Dependent on time. So that's dV dt in math terms or math notation. The rate at which the volume is changing. I'll leave the units out for now, and we'll bring those back in with our final answer. What are they asking me to find? Determine the rate at which the radius of the balloon is increasing. Well, that's dr dt, right? The rate at which the radius is increasing. And I have one more bit of information there, that the radius is 10. Now I had to think about that for a minute. They gave me diameter just to trick me up a little bit. So I have to realize that the formula depends on the radius, not on the diameter. And we know that the radius is half the diameter. Okay, so r is 10. Step 1 is done. That's all I'm always going to do. I need a formula to differentiate. Need to figure out what they're giving me. Often they'll give you one rate or two rates, and you'll have to find a third. And they asked me what to find. They asked me to find dr dt when r is 10. Alright, so next up is I have to differentiate this formula. Okay, and we're doing differentiating both sides with respect to t. Remember, that's really important, respect to t. We're considering our independent variable to be time. Okay, so I'm going to rewrite this. I'm going to go to the pen. Volume is 4/3 pi r cubed. Differentiate both sides with respect to time. So that gives me dV dt equal to 4/3 pi. Differentiate r cubed. That's 3r squared dr dt. Clean that up a bit. And my formula then, after differentiation with respect to time, is 4 pi r squared times dr dt. Okay, that is a formula that relates the rates at which the volume is changing and the radius is changing, and also still includes my distance value of r. Okay, third and final step will be to take that formula and plug in what we know. So we know that dV dt is 5, and this is the process you'll be doing for any of these problems. R is 10, dr dt is unknown. At this step, step 3, when you plug in your values that you know, there should only be one unknown value, and in our case it's dr dt. Okay, for every problem this will be the process. Sometimes you might have to think a little bit of how to get all the unknown values except for the one you're trying to solve for. Alright, so with a little bit of algebra, I can solve this and get my solution. That should be 400 pi dr dt. Divide both sides by 400 pi, and I get dr dt is equal to, if I'm dividing both sides by 400 pi here, then I can clean that up, and that reduces to 1 over 80 pi. And I'll bring my units back in, and if the volume is increasing by cubic centimeters per minute, then the radius should be increasing by centimeters per minute. Okay. A nice statement like the rate at which the radius increases is 1 over 80 pi centimeters per minute when the volume is increasing at a constant rate of 5 cubic centimeters per minute. Okay. Quick review. There's the problem. Step 1, write down what you know. Step 2, do the calculus. Step 3, plug in the values you need and do the algebra. Okay, so here is your problem to attempt. Follows that same 3-step process. We'll talk about this one later.